Welcome back to another video. I haven't made one of these for a while, but now that I'm taking over some content from Math Methods, we're going to have a look at Chapter 4a, the area under the curve. So you find that in your Hasty textbook. We're now moving on to Chapter 4, the first part, area under the curve. All right, so I'm just going to go straight into example because this is almost self-explanatory what we're trying to do here, but the techniques we'll just need to have a little bit of practice to master them. So we have a graph. So our graph, I'm using the same one as they do in their examples. Y equals x squared plus 1. All right, so we're going to consider the area under the graph from 1 to 4. So x equals 1 to 4, I should say. And I've made a mess of that, but you can see that here. So what I've drawn the graph and I've just marked down my boundaries of 1 and 4 and I've filled in there. So that's, if I could work that out, that is what I want. But what we're actually going to do initially is we're going to estimate it using rectangles. So this is the technique we do that's going to lead us into other concepts later on. All right, so let's say if we wanted to do this by one rectangle now, but you can see you can draw a rectangle like from this point here and go across, but that'll cut out this area here. You could also draw one from that point across and down, but then you've got extra area. So basically we're going to come up with an estimated boundary that the true area will fall in the middle of. So also, if I was going to use one rectangle, I can draw something up here just to fill up that rectangle, so like that. So that has a height of, we'll work that out in a minute actually. So our upper rectangle, get rid of that, it's not quite what I wanted. Okay. I'm going to do something a bit further with that. Yeah, that's what I want. Let's make it yellow. All right, that's too thin. Okay, let's try that out. Yeah, that's pretty good. It's clumsy with the mouse, but we'll make do. All right, so anyway, let's do here. I'm actually going to write this out anyway. So one rectangle. All right, so that height, so rectangle, length times width. The length across here, we've got the spacing is 3 times by the height. The height for the large rectangle is this point up here. So that's f of 4. Okay, the function 4. Oops, I'm getting ahead of myself. I'm about to write the answer. That's not the answer anyway. 4 squared plus 1. Okay, so 17. 4 squared plus 1, 17. 17 times by 3. Get my calculator out for this. TI, where are you? Where'd you go? There you are. Okay, so we can just go in. Use our calculator some time. So I don't have my headspace for doing 17 times 3. I hear you all say that is 51. All right. Okay. So for our lower, all right, again width of 3 and a height of, now in this case, that point there, 1 squared plus 1 is 2. So 1 squared plus 1 is 2 times by 3 is 6. Now that's a big gap between those two values. That's huge. All right. So let's see if we can do better than that. Let's at least use 2 rectangles. And what do I mean by 2 rectangles? Well, let's draw these. So if I was to do the lower rectangles, I'll just go across and then down. Okay, there we go. And then, all right, then I'll go, the second rectangle would be from there across. Okay, so that's a lower one. So you'd fill that in. All right, then I have to consider, okay, then what are my heights at this point? Well, that's 1 and that's 4. Okay. You know what? Let's skip that because I'm going to do what they did. I just realized the number's going to be messy. So if we take it 3, that sounds a little bit more natural for because we've got, then we could use numbers for each of these. Let's make that a tiny bit smaller. Okay. All right. So we've got a point of 2 and a point of 3. So the lower rectangles would be there across and there across. There's obviously not very good looking rectangles. Probably better off just doing this by hand. All right, but in any case, there's your rectangles. That would have, okay, so if that's 2, that's 3. Then you have a width of 1 and a width of 1. They should all be consistent width in terms of that. So, but then we do them with 3 rectangles. All right, so what would that look like? Well, let's do, well, I wrote up and lower. All right. So, don't need you anymore. Get rid of that anyway. All right. So in the case of when you talk about upper, all right, we've got 3 ones here. So we had the high values of x. So there was 2, there was 3. Okay. So if you're moving there, so the first rectangle has a height of f at 2. Has a width of 1, so there's your width, times by f at 2, plus width of 1 times by f at 3, plus width of 1 times by the function at 4. So those are actually the 3 rectangles for the upper rectangles. The lower rectangles, 1, 2, and 3. So width of 1, height of f at 1, width of 1, height of f at 2, width of 1 times height of 3, and so on. Now, you see they've done this. I'm just going to take their answers because I've already done this one. So that one is so that's 17. Or the no, that's the wrong one. That's 17. Okay, so that's 1, 2, and 3. And you see on the next page they've done the other one. They've done f at 2, 3, and 4. That's 32. So you see we're closing the gap on this. They've also gone and done this one subdivided into 6 units. You see you're getting much closer. Okay, now I'm going to stick with this example, and we're going to go for a much larger number. Actually, they've done, they've gone and done this. Basically, the more rectangles you use, the closer the approximation becomes, and the width between these answers decreases until you converge onto an absolute value that we'll come to later on. But let's have a look. I'm going to show you this area finder they use for the purpose of this. You need to know how to do this by hand. This is just a little bit of a bonus for our understanding. So we're just going to go from here. We're just going to add 1 to this little function machine. Okay, and there's our graph. Okay, we can also just take the little section we want. And we actually want to go from, well, I'll graph it from 0 to, let me say 4. Let's graph it a bit more. Let's go 0 to 6. Okay. Actually, no, we want area. We want 1, 2, 4. That's what we wanted in the first place. All right. All right. So, okay. There we go. So we're under this curve here. Now, there's a few little tools you can actually use and work it out. So the area between, you actually got exact answer 24. I'll explain to you how that works later on. At least we'll be able to do the calculations for that. But that's something we're leading to in a future lesson. Now let's use a rectangle rule. Okay, so in the first exercise we found partitions. We did it with 3 and did it from 1 to 4. If we do our upper calculation, find area. So yep, that's the 32. That's what it looks like. And the lower was that 17, as we got in our notes. So what if I was then, I'm going to break this up into, instead of 3, we'll do it into 30. Let's work out the numbers there. So if you use 30 rectangles, all right, the lower, so I'm just going to jump and put this in my notes as well. So lower is going to, so area is between 23.2 255. For the purpose of this, I'm going to hold on to those numbers because we're going to get close to a particular value. And if we go with the upper, we get 24.755. Okay, so I'll put that in my notes in terms of this. Let's go back to that. So yeah, so 30, and we got, that's where we are at this point. And then you can just keep scaling this up. I mean, now we're using technology, we could scale that up to something else. Let's have a look what this does. Oops, not that one. We want it's part of this anyway. Yes. Okay. 300. Let's go to 300. Fine integral. Okay. That was the upper. So 24.0751. And the lower, 23.9251. Okay. You get the idea. We're basically converging. Now, so the activities are you're basically working on things of this nature as well. Either you doing this by hand, just working out the rectangle areas for some simple calculations, or you might be asked to go and work this out using some sort of software package like this one. This is probably the easiest way to do it. Just use this one that's attached to this program. Otherwise, you'd be doing it with some sort of you'd be doing something like some sort of spreadsheet type program. I can demonstrate that if people are curious, but at this time we'll just use this one. All right. So what we're basically doing here is we're moving towards the definite integral. All right. So definite integral is basically as if you consider it this way. If I go back to here, if in the case of n, the number of rectangles approaches infinity, kind of the area approximation approaches what we call the definite integral. It looks something like this. So our definite integral would be 1 to 4 of the function of x dx. Now, so what this is, okay, so this is, remember, this works out the height of the function. We're going from boundaries 1 to 4. We're summing them all up. This symbol, the integral symbol, actually comes from the summation symbol that you can see over here. And then that is the infinitely small width of these. So you've seen the dx when it comes to differential calculus. It's like really small step of y with really small step of x. So this is the area for very thin widths, infinitesimally thin. Okay, so that's what we're approaching as that goes. So yeah, now we can work this out exactly. Now, how do we do that? Well, one way we can do that on a calculator. Before we actually learn how to do this other ways, let's see if I remember how to do this. We actually already know the answer, which is 24 when I loaded the program, but let's show you how we can get that. So if you want to find it by direct calculation, you can do this. All right. I'll show you a couple of ways, but we'll start with the first one. Let's see if I remember how to do this. Math. Okay, yes, integral. Okay, number 9. All right, there we go. And we got a little integral function. So we're going to do the function we're just looking at. We're going to go from 1 to 4, like such, and we're going to put in our function. So we put our variable squared plus 1 and d variable key, important. And what do we get? We get 24. So yeah, that is actually equal to 24. All right. Now, so that's how you can go about doing the calculations for these. So you do need to know how to do that on your calculator because there are some ones that we cannot analyze by any other means. So if you look at the second section of work, so exercise 4A.2, you are graphing. You can graph things on your calculator to sketch them, graph the area enclosed, and then you can also use some sort of software package to do upper and lower or rectangle sums using the area package or otherwise. All right, so I'm going to take this question 3 though, because that's an interesting one. I want to look at that. I believe you can't solve that using the algebraic techniques we're going to teach you later on. I think that is a one that we cannot solve. All right. Okay, so we're going to graph that. Graphing package, calculate upper and lower rectangle sums. Yeah, you can use the graphing package to do that. I actually just want to go and graph it on here. I want to go and look at this, look at the symmetry of it, and then also, yeah, I want to actually find the exact value. All right, so, okay. All right, so let's go to e to the x. That's the one I want. Yeah, there we go. All right, so we've got e to the x minus, all right. Now I'm going to make that a little bit bigger because I'm going to try reading it as e to the x over 2. Let's not do that. Let's go a bit larger. Yes, over 2. Okay, so I think I can just do it this way. That's squared divided by 2. That should work. Okay, now when I graph that, let's have a look. Yes, I'm going to make my window a bit smaller. Now, if you've done normal statistics, and you should have at some point, you might remember this as the bell curve, which is more or less what we're looking at. So we're going to go from, let's remember, do -3, and we'll do 3, and we don't need any negative space. That's asymptotic there. I don't think we need much in way of this. I'm going to put that at 2. I think that's well enough. There we go. Yeah. So basically, we want to find the area under this. I've actually done it from -3 to 3, so finding the area under this curve. Okay. Now, so I'm going to see if I can actually do it with the graph section, which I think I can. Yeah, here we go. There's another way you can go about doing it. You can actually do here. Let's do a lower limit. Lower limit, I want that to be -3. Okay. Upper limit, let's go to 3. And there you go. It goes and works it out. So there's actually approximately 2.5 thereabouts. I think that's all right. So yeah, and actually notice there, because it's symmetric, they actually get you to work out on one side and then the other side. Yes, there is a this is actually mirrored on the it's an even function, thereby it's mirrored on the y-axis. So if you work out, so not surprisingly, I could just do that here. I could go and let's just go from 0 to 3. 0 to 3. Okay. Well, for some reason it's still showing the whole thing again, but let me just replot that. Okay. Why is it still all filled in? I don't know. Let's ungraph that. I don't know why it does that. That's better. Okay. Now can we see it without? There we go. We're back there again. Okay, and then we can just do. I thought it would reset after you do that once. So let's do 7. Let's go from 0 to 3. Yeah, and that's half of it. And then because it's the same on the other side, it's an even function mirrored on the y-axis. So if you double that, so approximately 1.25, double that is 2.5 as we suspected. That's basically what we're doing here. Except I just skipped the having to do all those rectangles, and I just got it to do it. It basically works out like the calculator actually does a rectangle or similar type of technique. It just does a lot of them because it has a lot of processing power. So that's really that as far as that stuff goes. Anything else that's surprising here? Okay. All right. Now. Okay, so actually learning they're showing a couple of rules here where basically the idea, like if you work out the area from A to B and B to C, then you can work out the area from A to C. So I might even just take out that concept. Let's just do one more task before we wrap this up. Okay, so where is my projector? There it is. Okay, so let's get a new page going. All right, so I'm just going to have a look at question 5. Use the diagram alongside to show for any positive function f of x. Okay, all right. I think the first part, okay, so actually these are rules we will derive later on and we'll state explicitly. But basically, if you haven't moved, if you've got no width, this is kind of self-explanatory because essentially because it has width of 0. All right, I think that makes sense. If you go from A to A, you haven't moved anywhere, so you've got no width. Width equals 0 times by height is still 0. All right, so that's all right. Now this one, okay. The second one actually is also pretty self-explanatory. Like the idea that you have this graph, so the graph here, and you've got this area, this area, this area. All right, so you've got A, B, and C. Okay. So let's call that area 1, that's area 2. So the integral from A to C of f of x dx is essentially the sum of the other two areas. Because you're going from A to C, you're adding all of this up. So thereby, that's also equal to the integral from A to B plus the integral from B to C, because those are the individual areas in that graph. Okay, so I think that makes sense. That's pretty self-explanatory. And then you can apply that for part B. For a positive function f of x, 2 to 5, f of x equals 10. So you're not given a graph, but you know it's positive, which means it doesn't go below the x-axis. That's important for reasons we'll go into another time. And 5 to 9 is 12. Okay. All right, the first one, pretty obvious. We go from 5 to 5 of f of x. We don't even need that information. That equals 0 because you haven't gone anywhere. The other one, from 5 to 9, from 2 to 9. Okay, so from 2 to 9 is the same thing as going from 2 to 5 dx plus 5 to 9. And then that is equal to 10 plus 12 is 22. Pretty simple. All right, so I'm going to wrap it up here. Have a try for yourself, and we'll go on with anti-differentiation next time. Okay.